Okay. Okay. Piotr, you can start. Please unmute yourself.
Okay, so good afternoon, everyone. We started the recording of this event, and this is the second part of InfraChip Digital School on Power, organized by Cesamat. Just a short reminder: Digital Schools is a series of webinars organized within the InfraChip Power project and dedicated to different cutting-edge advancements in technologies. This webinar is related to the emerging photovoltaic solutions, perovskite solar cells, high power transistors, and innovative approaches for ultra low power electronic devices. We start our afternoon session. We will have two experts from leading institutions that will present their research. The first one is Maciej Haras from Warsaw University of Technology that will present the research on entitled New Paradigm for Powering Ultra Low Power Electronic Devices. So Maciej, please, you can share your presentation and start your talk.
Okay. Thank you, Piotr, for introducing me. So my name is Maciej Haras, and I'm working in two institutions, mainly Warsaw University of Technology, Center for Advanced Materials and Technology, CESAMAT. And I'm also affiliated with Gdańsk University of Technology, Faculty of Electronics, Telecommunications, and Informatics. And I am here today with you to present you my presentation titled New Paradigm for Powering Ultra-Low Power Electronic Devices. Digital school is still a school, so I'll be very didactic, trying to be synthetic at the same time. So in order to give you this presentation,
Maciej, you're muted.
Okay, I have to restart. Sorry, I haven't seen that. I am coming back. So I am affiliated with two institutions.
No. This was already done here.
This was okay. I don't know why.
Yeah,
I don't know why.
Just a couple of seconds we missed. So
okay, so I divided my talk into four main blocks in order to give you this presentation in easy to get and readable way. I will start with broader context. Then I will switch to this new paradigm of powering. And in the third block, I will highlight conventional energy harvesting techniques. And I will complete my talk presenting some future prospects and some innovative approaches in the field of energy harvesting. So let's start with the first block, the broader context. So as you know, our humanity, industry, economy requires more and more energy. In 2023, we have consumed nearly 15,000 million tons of oil equivalent of primary energy. This is entire energy, including electricity, heat, biofuels, etc., etc. Nevertheless, it is huge amount of energy we are consuming each year. Inside this primary energy, one of the components of primary energy is electricity. And in 2023, we have generated nearly 30,000 terawatt hours. So huge amount of power we are consuming and generating. And this has negative impact on our environment. Here, I don't know, I hope you can see my cursor. Yes, I hope so.
Yes, you can see.
Yeah, okay. So here on this plot, you can see historical evolution of carbon dioxide concentration in the atmosphere and the average temperature of air. After 1980, you can see that the air temperature is growing very fastly, as well as concentration of carbon dioxide. The second consequence of increasing demand in energy is that we need to extract our fossil fuels, especially in countries such as Poland. We are producing around 90% of electricity from coal and gas, some from fossil fuels. Here you can see the perspective how the depletion of natural reserve is occurring. We are now crossing the maximum, and we need to start dig deeper and deeper in order to extract the coal. It will be more expensive and more expensive. On the other hand, we are observing huge progress in semiconductor industry, and this progress has many sides. I will only focus on three. Firstly, we have a huge economical boost, economical progress. Here you can see historical evolution of average transistor price over the years, over last 2 decades more or less, and you can see that the average transistor price was reduced 1,000 times. At the same time, we are capable to increase the production capabilities, which is presented in this magenta line. And owing to that, the semiconductor industry showed astonishing compound annual growth rate, 8.5% over last 5 decades, more or less. So this is something unprecedented. Why such a big achievement was possible? Well, one of the reasons is the Moore law, also called in our field the miniaturization. And this is this Moore trend you can see on this plot. On the blue one, you can see the MOSFET gate length. And you can see that in 1970, the MOSFET gate length was 10 microns. Now it is few nanometers. So transistors are getting smaller and smaller. The Moore law says that each 2 years you have to produce 2 times smaller transistors. It's no longer in use, this law, but it was a law for 40 years. Producing transistors smaller allows us to pack them more and more in one chip, and this is very attractive. But this is not the only one advantage. Another advantage, making the transistors smaller and smaller, is that they are requiring less and less energy to operate. On this gray line, you can see how much watts per million operation per second is needed for a chip. And on this plot, you can see how different technological trends improve the energy consumption per switch. So now, for transistor to perform single switch, we need to have around 1 attojoule of energy. Very small amount of energy needed for performing single switch. So we are performing devices small. We are fabricating devices smaller and smaller. They are more performing. They are less energy consuming. And this allowed to emerge new markets. And one of the branches that appeared owing to those fantastic achievements in the semiconductor industry is the Internet of Things. Historically, it arises from the concept of intelligent building. It was early 90s. So you have multiple sensors which are distributed, spread around your building and inside your building. And those sensors are providing some information that are measured in your building, like temperature, presence, is the light switched on or switched off, is the heating switched on or switched off, and they are communicating those measured data to the controlling unit, and the controlling unit takes control over the object. This is the concept of intelligent building. This concept is sorry. The IoT right now is the main driver for the entire semiconductor industry. Here on this plot, you can see historical evolution of IoT devices quantity compared with human population. This is this magenta line. We are somewhere in the middle between 2020 2030. So for each one of us, there are more or less 3.3 IoT nodes. Okay. They are outnumbering human population more than 3 times. But there is another paradigm or another novelty that IoT introduced to the semiconductor industry. We are used to the situation where the electronic devices are operating continually. You switch on the device and it remains on till you switch it off. Well, in IoT, we are operating devices differently. We are operating devices in cycles. So when the controlling unit triggers on the sensor and asks for example, temperature measurement in the room, the node is turned on, it measures the data, then it codes the data and transfer it to the controlling unit, and then it goes idle or it is switched off. Entire cycle consumes less than 100 microjoules, so very small amount of energy needed to perform one cycle of operation. We are now facing, due to the huge quantity and miniaturization, we are now facing the conventional supply bottleneck. Imagine that you are in the factory, and inside the factory or in the production line, along the production line, you have thousands of sensors. Each one of them has to be wired, has to be supplied. And this is problematic. The same thing occurs in the automotive industry. There are more or less 80 sensors in the medium class car and 80 controlling electronic control units. And each one of them has to be supplied. Conventionally, we are supplying our electronic devices using batteries and wires, but regarding the quantity and size, and especially the power consumption needed to supply the electronic devices, it is not longer a good idea to supply the electronic devices using batteries or wires. Firstly, batteries are requiring periodic maintenance and replacement, which is costly. And secondly, they are producing battery trash. And here you can see the Eurostat statistics, how much batteries was put on the market during the years. So those are those red bars. And in 2021, there was nearly 250,000 tons of batteries that were sold. And we are recovering only 50% of them. And still Europe is kind of a leader in terms of green energy, recycling, etc., etc. What about of the rest of the world, the countries like China or US? Sooner or later, even if we remain on this 50% of recovery of waste batteries, we will end up with drowning in the sea of used batteries. So you might feel confused. We are now in the situation where there are two universes. On one hand, we have huge energy demand, energy production in terawatt hours, and then we are converting this energy. And even assuming that we are converting this energy with 99% of efficiency, because we cannot convert any energy without losses. So even 99% of efficiency, which is very optimistic, produces losses counted in terawatt hours per year. On the other hand, the second universe offers more and more efficient devices, smaller devices that are requiring very small energy to operate. And this is a very convenient situation to use those losses generated on the macro scale to supply those small electronic devices, small energy demanding devices. And this is how energy harvesting was created. The energy harvesting is energy extraction from ambient or waste energy sources, so naturally provided energy or waste energy. This is Wikipedia definition. Okay, let me now go to the next part of my presentation, where I will present this paradigm of powering, and especially focusing on the losses availability. So we are consuming different types of energies, and we are producing a lot of different types of losses. Here you can see one example of a medium-sized truck, and as you can see, providing 100 kilowatt of energy, of power in fuel, results only in 25% of efficiency. All others are losses for exhaust gas, for cooling, for other things that are occurring in the car. All those losses can be at least partially recovered using energy harvesting. Another good example are our houses. Here you can see a typical Polish house where there are many appliances, there are heat flow, there are radiators, there are liquid and heat, liquid and fluid flows. We have sunlight, vibrations, we have radio frequencies. All those energies, or all those different energies can be converted into useful electricity. On this plot, we can link the typical consumption for different electronic devices like temperature, event control devices, RFID, LCD, etc., with typical energy generation provided by conventional energy harvesters. And our range of interest starts from 10 nanowatts to 20 milliwatts. This is the range of IoT and low and ultra low power electronics. As you can see, energy harvesters can cover totally the energy requirements of multiple electronic devices. Is it important? Well, this conglomerate of needs and requests from electronics industry results in very huge interest in energy harvesting. So I put to the Scholar and Google patents this query, energy harvest or harvest energy. And it gave me those two lines. The first red line is the patenting activity. So you can see there are patents in the field of energy harvesting that are submitted in thousands of 1,000 patents per year, and we have also 1,000 publications, book chapters, conference papers in the scientific activity. You might be surprised what happened here in around 2019, why the patenting activity is collapsing so abruptly. Well, this is due to the COVID situation where a lot of companies were bankrupt, a lot of companies had contingency plans and had had to reduce the employment and labor time. So let me now go to the third part where I will highlight very synthetically conventional energy harvesting techniques. Here you can see the plot that is summarizing conventional energy harvesting techniques: thermoelectric, photovoltaic, radio frequency, electromagnetic, piezoelectric, and electrostatic. There are many more techniques, but those 6 are known, are defined as a conventional. You can see that some of them are producing DC output, some of them are producing AC output. Some are dedicated to convert mechanical energy like vibration, some convert light, and other convert heat. So we have to adapt the energy harvesting technique to our energy source. So I will go very briefly through those conventional techniques, starting with rotary electromagnetic. So this is the harvesting which every one of us was using. It's electromagnetic induction defined by Faraday law. It's very mature technology and physics. It produces the highest power densities among all methods, starting from microwatts per centimeter cube per cubic centimeter to 5 milliwatts per cubic centimeter. And I'm sure that you have used that. If you are confused, I will show you an example. So this is electromagnetic rotary harvester, but it's very cumbersome. It's very big. People now are doing something smaller. So one of the pioneers in the field of miniaturization of electromagnetic harvesters was Seiko. They developed a generator that was integrated in the wristwatch. But now there are some micro wind turbines that are that are fabricated, and they are cooperating. They are converting the airflow in the building, like air conditioning. They can produce really high power, like 8 milliwatts or 20.5 milliwatts, and they are very small. The biggest drawback of electromagnetic harvesting is that they are incompatible with CMOS, with large-scale production, and they are quite complex. Their construction is quite complex. We have to fabricate the winding, the shaft, the bearings. It's very manual mechanical work. So it's difficult to fabricate them on the large scale. Another group of harvesting, which is very popular, are piezoelectrics. So this is also very old effect, discovered 200 years ago by Curie brothers. And so there are specific materials which are responding with voltage when they are submitted to the mechanical deformation or mechanical stress. There are many realizations. They start to be CMOS compatible. They have AC output, and they are very dependent on the acceleration and frequency of the vibration they are converting. So one of the nice examples was GPS localization system that was powered by the piezoelectric generator. It was integrated with the shoe heel of the soldier, so we were always capable to localize the soldiers on the battlefield. Soon after, it went to the civil market, and now you can buy the shoes for runners. They can calculate your footfalls. They can calculate your calories due to the thanks to the piezoelectric harvesting, which is in the heel. Another very interesting group of harvesting is electrostatics. Those are basically variable capacitors. The biggest advantage of those harvesting technique is that they are CMOS compatible, fully CMOS compatible, and they can be easily miniaturized. However, they are producing very small powers, like from 1 to 600 microwatts. There are many topologies of them. The most popular are those depicted in E and F figures, like interdigitated fingers. And this was fabricated in the CMOS factory and can be integrated with monolithically integrated with the integrated circuit. However, low power that they are offering is precluding their popularization on the market for a moment. One of the first realization was the bitrate, the hard bitrate monitoring of a goat. So this can happen only in Japan. It was the group from Japan. So they installed the electrostatic harvester on the heart of the goat, and thanks to that, they were capable to monitor how fast the heart beats. The next group is radio frequency, is the subgroup of electromagnetic harvesting, but dedicated for very specific energy source. So this energy source is very convenient. It is wireless energy, Wi-Fi or GSM. And on this plot, you can see what is the RF power density for different environments like city, rural zone, and different measurement spots. And you can see that we are oscillating somewhere between 0.1 to even 10 milliwatts per meter square. So huge amount of RF power density. So this is very convenient wirelessly transferred energy. It has AC output. However, it is quite complicated to construct the harvesting system. You need to build an antenna. This antenna has to be matched with the wave. Then you have to rectify it. It's high frequency rectification. There are many blocks to actually extract this energy from Wi-Fi, for example, and store it into in the energy buffer. And therefore, overall efficiency of those harvesting techniques is very low. Nevertheless, there are some realization, and this is one example. This is the Wi-Fi powered clock. It's equipped in 8 antennas, and those 8 antennas are capturing the Wi-Fi signal and are powering the IC that is driving the clock. The biggest group in the energy harvesting, the most popular, are the photovoltaic. They are definitely CMOS compatible on large scale. We are producing them from micro to megawatts. They are providing DC output, and they have very high power. They can generate very high power. So I will not go into the physics. You probably know all that. But I would like to highlight something very important. You can see here this plot of photovoltaic power generation in different countries over the years. And suddenly, somewhere between 2005 and 10, it exploded, okay, somewhere around 2005. And this is linked with CMOS compatibility with monocrystalline silicon production of photovoltaic cells. CMOS compatibility allows us to dramatically reduce the cost of devices and spread it over a large market. Therefore, owing to this CMOS compatibility and monocrystalline technology, the photovoltaics became very, very popular. There are many examples of of photovoltaic harvesting, starting from micropower to more sophisticated, like those codes for bike riders. And now I will focus on thermoelectricity. So just to remind you, this first slide or the second slide of my presentation, we are consuming a lot of primary energy, almost 15,000 megaton of oil equivalent in 2023. However, we are at the same time wasting a lot of energy. So from 20 to 50% of this primary energy was released as a waste heat. And when you look on your daily lives, you can see that there are many situations where we are losing a lot of heat. We are losing heat in our households, in our cars, our factories and industry also releasing a lot of heat, and all the electronic equipment. All those heat losses can be recovered using thermoelectricity or thermoelectric effect. So thermoelectric effect is also a very old effect. It was discovered by Thomas Johann Seebeck almost more than 200 years ago. So how it works? So during when you submit the rod of semiconductor over the different temperature, the majority carriers are migrating towards colder side, producing the potential difference VP and VN. Here you can see on this slide the typical conventional topology of thermoelectric generator, which is called P-type topology. You can please note that the two thermal legs are electrically connected in series, which is marked by this current flow, and they are thermally connected in parallel. This is single-step conversion, very reliable, vibrationless and noiseless. It has CMOS, it has DC output, and it starts to be CMOS compatible, but only when we are using nanostructurized materials. It is available in range of microwatts to kilowatts. Due to vibrationless and very reliable operation, it was always used in sophisticated military or space missions, like in the late 70s, it was installed in Pioneer 10 satellite. And even now, there are two rovers on Mars. One is Curiosity, and the second one is Perseverance, and they are equipped with a radioisotope thermoelectric generator as well. So what is the future of harvesting? I will now focus your attention on something more unconventional and innovative in the field, starting with thermoelectricity. So thermoelectric effect, as I said, is single-step conversion. So entire conversion from heat to electricity is happening inside the material. To compare performance of different materials in thermoelectric applications, we are using so-called non-dimensional figure of merit, which is marked ZT. It depends on the Seebeck coefficient, electrical conductivity, and thermal conductivity. As you can see, that fantastic thermoelectric material should be like a crystal for current conduction and like a glass for heat conduction. We call it a funnel glass electron crystal material, the material which does not exist. When you look on this plot, you can see that the semiconductors are offering the optimal compromise between those antagonistic parameters, thermal and heat transport, and they are the best for thermoelectric conversion. Why ZT is so important? Well, it is so important because The efficiency of thermoelectric generator depends on the temperature, the externally imposed temperature, and ZT of the material that is executing the conversion. And here you can see the efficiency of different conversions like solar, geothermal, Rankine, etc. Compared with thermoelectric state of the art. So we have now materials that with ZT something between 2 and 3, but still it results in efficiencies around 20% max, maybe 25, very low efficiencies, making them unpopular on the market. Optimizing this ZT is very difficult because those parameters have antagonistic behavior. Here you can see the historical achievements in the field of optimization of ZT for different materials. And I would like to underline that it took more than 30 years to produce material that ZT surpasses 1. Currently, we are something between 2 and 3, but we still need to do a lot of work in the field because we are looking for the material that ZT with ZT at least 4, that will be a launching point for popularization of thermoelectric devices. The second information is that most of thermoelectric materials are very complex, harmful, and toxic, and especially incompatible with CMOS technologies. So one of the innovative tracks would be to replace those conventional thermoelectric materials, lead, bismuth, antimony, and tellurium. Those are most popular. They are toxic and harmful, and we can replace them by silicon and germanium, which are easy to get, cheap, and environmentally friendly. But most of all, they are offering another important advantage. Most of the biggest players are using CMOS. Those materials, those conventional thermoelectric materials, are incompatible with those technologies, and therefore resulting in very high cost per kilowatt, even going to 15,000 euro per kilowatt. On the other hand, silicon germanium and silicon germanium are compatible with CMOS, and owing to the large-scale production, we are capable to reduce the cost per kilowatt even down to 100 euro per kilowatt. This is very attractive. How to make CMOS materials like silicon attractive for thermoelectricity? Well, we need to reduce this very high thermal conductivity, and we know how to do it. When you use thin film silicon with the thickness below 1 micron, you can see that we are observing this reduction of thermal conductivity, and this is the effect that can be employed in the production lines. Another path for thermoelectricity to be more popular is to change the conventional P-type topology, which is not very convenient and not very good for large-scale CMOS production, because it is a topology which is vertical. CMOS factories don't like that. We would like to have something which is lateral, and this is topology of lateral thermoelectric generator. It uses thin film semiconductors to take advantage of this thermal conductivity reduction I have just presented. It redirects the heat flow because the hot spot is here on the bottom, so it redirects the heat flow from vertical to lateral. And owing to the use of thin films, we are capable to integrate mechanical flexibility and mount them on the curved surfaces. What to do when our market is already flooded with conventional thermoelectric generators, which are using bismuth and tellurium mostly, and how to improve their performance? The third path we can adopt to make thermoelectric more popular on the market is to improve their working conditions. When you analyze this formula, you can see that the output power of thermoelectric generator depends on average Seebeck coefficient, resistances, the load resistance and the internal tag resistance, and the effective temperature across the generator. When we want to improve this power, we have to raise the Seebeck coefficient, but this user cannot do. This is material property. We should work with the resistance matching conditions, so the load resistance should be equal to the internal generator resistance, but this is already on the market. This is commercialized. It is called maximum power point tracking, and they are integrated circuits that are providing that. And the third strategy would be to increase the delta T effective across the generator. And this is what we did here in Cesamat. When we are operating a conventional, the thermoelectric generator in conventional way, you can see that at the beginning, you have huge peak of power, and then this power drops to almost to zero in the steady state. This is due to the negative influence of thermalization. So at the beginning, the difference across the temperature difference across the generator is very big, resulting in very high power. In steady state, this temperature difference across the generator disappears almost to zero, and in steady state, your generator produces almost zero power. How to reduce this? We have proposed the method, a technique that reduces the negative impact of this thermalization, so the disappearance of this delta T effective. In order to do that, we have come up with the idea to periodically connect and disconnect the thermoelectric generator with the heat source. We are using for that the bimetallic strip that is performing flexions when heated, and it lifts and lowers the generator over the heat source. So it is periodically connecting and disconnecting the generator with the hot temperature. This strategy produces around 3 times more power than conventionally operated, continually heated thermoelectric generator. And it was published in Nano Energy a few years ago. It is very promising, and still there are things to be explored. It's not, it is not the most optimal point. I am going back to this figure I have presented that is highlighting conventional energy harvesting techniques to introduce some more futuristic and more innovative energy harvesting techniques. When you look on those 6 methods, you have to say that all of them are dramatically depending on the quality contact between the harvester and the energy source. For example, piezoelectric generator has to be as tightly as possible connected with the vibrating source. A thermoelectric generator, the same. It depends dramatically on the thermal resistances between hot source and the cold source, etc., etc. The photovoltaics has to be at least oriented towards the source of light. All of them are depending on the contact quality or at least orientation towards the energy source. And this is very limiting. This is something we want to avoid or we want to solve. We would like to have the harvester that it can work always and everywhere. And this is something we are exploring now in the in frame of ERC advanced grant project called Sphinx. This is Professor Skotnicki project. So what we are proposing. Probably all of you know this historical monument. If not, this is Mont Saint-Michel in Normandy, France. And there are 2 photos. One is taken in when the sea has low tide, and the second photo is taken when the sea has high tide. The tides of the seas and oceans is very well known. For ages we know how to do and how to calculate the sea level depending on the moon phase, but you might be surprised that the sea and ocean is not the only media that is behaving in tides. Here you can see the recording of temperature difference and pressure difference each day in 2022, starting from January, ending in December 2022 in Warsaw. And you can see that each day produces a pressure difference and temperature difference. We made some statistical calculation, but over 3 years, not 1 year, and it revealed that we have those variations of pressure and variations of temperature. Statistically, it gives something that resembles tides. There are 2 maximas and 2 minimas for pressure tides, and 1 minima and 1 maxima for temperature tides. 1 minima just before the sunrise and 1 maxima around noon. Those data was collected for 3 cities in Poland: Gdańsk, Warsaw, and City of Hell in North Poland. We thought that this is fantastic source of energy, those variations, because they are occurring always, every day, everywhere on Earth. And we would like to use those variations to produce electricity. But how to do that? Well, you have those temperature and pressure tides, and we will use different liquids that are very depending on the temperature that they are exposed. There is chloroethan and chloromethane, which are the most promising, but there are different ones. So you can see that their vapor pressure is very depending on the temperature. What we are planning to do, we started the realization of this project in September last year. So the plan is to fabricate a harvester with a cavity filled with chloroethan, for example, chloroethan. And on the top of this cavity, you have thin film silicon or thin film bistable membrane covered with piezoelectric. While temperature and pressure changes during the day, this bistable membrane will perform abrupt flexions towards upwards or downwards, and piezoelectric will transform those flexions into electric signal. We have already constructed the mega or macro demonstrator. This is this big cap from brass, and we have some. We put it on the hot plate. This brass cap is covered on the top with a piezoelectric and bistable metallic disc, and this is the cross-sectional view. We have filled that with different liquids, with acetone, with alcohol, with isopropanol, and chloroethan. And we were changing the hot plate temperature. Here are our preliminary results. You can see that in this configuration, we are capable to generate the voltages above 12, 13 volts, around 12 and 13 volts, which is far enough for ultra low power electronics. And this is very convenient because those temperature and pressure variations will occur everywhere, always, each day. So it is quasi omnipresent energy harvester. Another and the last idea I will present today is the energy that the energy strategy, the energy harvesting strategy that uses Coriolis force. Coriolis force is usually linked with mega big-sized objects like tornadoes, clouds, typhoons. So on the northern hemisphere, you will have this direction of rotation. On the southern hemisphere, you will have opposite rotation of clouds and water vents. This is due to the Coriolis force. And we would like to use this Coriolis force while it is almost omnipresent on Earth. So we came up with an idea to use as a medium the electrically the carrier, for example, the electron. We put the electron between in the magnetic field, so it starts to so it is accelerated by the field and by the gravity. But due to the Coriolis force, its trajectory, it is not free fall, it is not straight line, but it is bended. It is tilted by the delta x, and this delta x is provided here. So it depends on the height, on the mass, and on the voltage you are applying between those top and the bottom electrodes. We proposed a topology of this sensor. It can be used as a position sensor, but it can be used also as a harvester. So you have top and bottom electrodes installed on the top and bottom of a vacuum box, and the output electrode, which is on the side. When it operates, the electrons are falling and touching the output electrode instead of falling towards the bottom electrode. This is the idea. We made some calculations and simulations, and we regret that we are, for a moment, it's impossible for us to make an experiment or a demonstration of this effect. So if you feel inspired, please check details in this paper. It is freshly published. And if you feel inspired, just contact me, and maybe we can make a common project and common investigation of this topology and this harvesting technique. As you can imagine, the signal is very small because the charge of electron and the mass of electron is very small. In order to boost the output signal, we can arrange the single engines in parallel and in series in order to boost the voltage. This will be the series configuration. And if we want to boost the output current, we will use the parallel configuration. So going to conclusions, we are arguing with fossil fuels in depletion. We are struggling with climate changes, and meanwhile, at the same time, modern electronics growth is slowed down by the lack of alternatives for batteries and wires. On this, we are consuming huge amount of energy, but we are at the same time wasting a lot of energy. That those waste are sufficient to supply different semiconductor devices, because semiconductor industry has outstanding performance growth, especially emphasizing the energy consumption. There are energy harvesting techniques and solutions that can totally supply various types of low power electronics. Conventional energy harvesting performance depends dramatically on orientation and contact quality with the energy source, and this is something we are fighting with right now. We need new materials, especially for single-step conversions, in order to make energy harvesting more popular. So we need new materials, especially for single-step conversions, new industrially compatible topologies like lateral tag, new mode of operations for conventional generators. An example can be a pulse mode of operation for thermoelectric generator. And we are aiming at development of new quasi-omnipresent energy sources like Sphinx or Coriolis force. Miniaturization and integration with integrated circuit is a holy grail. It will launch the energy harvesting on the market very abruptly, because entire electronic industry is waiting for monolithically integrated, self-supplied, energy-independent electronic devices. Thank you so much for your attention. If you have any questions, I will be happy to answer.
Thank you, Maciej, for a very inspiring presentation about different paradigms for powering the electronic devices. So I just remind the attendees that at the bottom of on the top of the window, there is a question and answer button that you can use to start typing the questions. Okay, so stop the presentation, Maciej, please.
Okay.
Okay, so let's see any questions. So maybe one question regarding these different approaches for the energy harvesting. So you presented different techniques, different ideas. In your opinion, which technique, which approach is most will be in the future most suitable for the integration with chips using standard CMOS techniques to power the sensors locally on chip. So what is your opinion from your presentation? I see that thermoelectrics is very promising, but maybe other techniques is also good for these applications.
Yeah, so to answer this question, for today, for now, photovoltaics is integrated fully in with CMOS, electrostatic. Yeah, and those two are the most compatible with CMOS for the moment, for today. There are a lot of effort put in integration of or fabrication of CMOS compatible thermoelectric devices, and this, I think, sooner or later will be exploding because we are generating a lot of heat in electronic devices. For example, I don't know, in microprocessor there is a lot of heat released, and thermoelectricity can not only be used as a harvester. This is the Seebeck effect, but it can be also switched and can be used as a cooler, and then it is Peltier cooler. It's very attractive for cooling very efficiently the microprocessors. And when the load, computing load, the processor load is lower, you can harvest some amount of energy, recover those heat. It is very attractive. I think sooner or later it will be exploding on the market. So for me, thermoelectricity is the next candidate to be CMOS compatible. There are some early birds because they are silicon-based thermoelectric generator, and especially silicon germanium-based thermoelectric generators. But the problem is to shift their operation temperatures from medium and high range to, let's say, something more suitable for electronics, because it's already high temperature conversion for both of them. But a lot of companies is working on that. STMicro, Samsung, those two I know for sure, and a lot of institutions like ours, as like our institution, Warsaw University of Technology.
Okay, thank you for your
Thanks.
answer.
Thanks.
I see. Okay, I don't see. A moment, it's loading. Okay, I don't see any questions from the audience, so thank you again for your presentation.
Thank you, Piotr.